In today's video, we're going to be talking about suspicious points. Suspicious points are points on a function that are a little bit hard to define. In other words, the rules change at a certain point, and this is a little bit easier to see with an example. So this is f of x, and f of x is a piecewise function. We have 3 minus x, and x minus 2 being our two pieces of our piecewise function. We use 3 minus x when 5 is less than or equal to x, which is less than 2, and we use x minus 2 when 2 is less than or equal to x, which is less than 5. So what I want you to tell me is f of x continuous? By the way, this is continuous. CONT with a period is just continuous. Is f of x continuous at x equals 2? So why am I asking about x equals 2 specifically? Well, as you can see, in this first function, we want x to only be less than 2, but here we want 2 to be less than or equal to x. So the rule changes depending on which function you're using. Let's draw a graph, as it may make it a little bit easier to understand this function. I'm going to draw it right here, and we're going to get the green pen out just for fun. Oh, and this should be a -5. I meant to put a negative there. So between -5, let's say that this here is -5, and this is 2, and then over here is 5. We have the function 3 minus x, which will look something like this. This is not an exact drawing, but it looks something like that. And actually up here, let me put a dot. So that's what this 3 minus x function looks like. And for x minus 2, this is only between 2 and 5, so that means our function starts here, right there, and then goes to 5 as so. Before we go too far, I want you to understand this graph. Here we have a closed interval because -5 can be less than or equal to x. Here we have an open interval because it's less than 2 but not including 2. Here we have a closed interval because 2 can be less than or equal to x. And here we have an open interval because 5 has to be less than x, so we don't include 5 as an endpoint. So now that we have a beautifully drawn graph, I know, I'm quite the artist, we can more easily figure out the domain of this graph. Remember, the domain is just the span of x values that our function crosses. So our lowest point is 5 and our highest point is 5. So our domain is between -5 and 5. Sorry, I meant -5. But we don't include 5 here because x is strictly less than 5. And here we include -5 because x can be equal to -5. Meaning that we put a bracket on this side to include this endpoint and a parenthesis on this side to not include that endpoint. So our domain is -5 to 5, including -5 and not including 5. So first of all, is x equals 2 in the domain? Well, visually it should be pretty obvious that yes, x equals 2 is in the domain. Mathematically, we can plug in 2 to either one of these functions and prove that 2 is within the domain. 3 minus 2 is equal to 1, and 2 minus 2 is equal to 0, which are both in between -5 and 5, so it's most certainly within the domain. And most obviously, of course, you can see it visually here. But in order to prove that this function is continuous, the limit approaching from this side and the limit approaching from this side have to be equal. If they're not equal, that means there's a jump or a discontinuity somewhere. And yes, I understand that we can already see that jump here, but let's do the math in case you didn't have this graph available to you. So first we want to find the limit as x approaches 2 from the negative side, which would be from here to here. Let's write that down over here. Limit as x approaches 2 from the negative side of 3 minus x is equal to what? Well, all we have to do is plug in 2 for our x value, which gives us 3 minus 2, which is equal to 1. Doing the same thing but coming from the positive side, we want to find the limit as x approaches 2 from the positive side, and from the positive side we need to use this function. By the way, the reason I use 3 divided by x is because we're coming from the left side, which is this function. But when we're coming from the right, we have to use this function, which is the bottom one. So here we'll write x minus 2. Once again, we just have to plug in 2 for x, so this turns into 2 minus 2, which is equal to 0. And you may notice that one of our limits is 1, and one of our limits is 0. These do not equal. Therefore, the limit at x equals 2 does not exist. We're going to write in green just for fun, D, N, E. The limit at x equals 2 does not exist. So what does this tell us? Well, we wanted to figure out if f is continuous at x equals 2. And if the limit doesn't exist, it cannot be continuous. So the answer to this question is no. F of x is not continuous at x equals 2. It's very easy to understand visually since we have this obvious jump here, but it's not too taxing to do it mathematically as well. Let's do one more example so that way you really get the hang of suspicious points. Our last example for this video is g of x instead of f of x. We're really changing it up today. And g of x is once again also a piecewise function. And this piecewise function is 2 minus x and x minus 2, and the function is 2 minus x when 5 is less than or equal to x, and when x is less than 2, and the function is x minus 2 when 2 is less than or equal to x, which is less than 5. So not very different than last time, but we have a slight difference mainly in our top function. So if we draw it here, we may be able to see something different visually. Let's draw our xy plane along with our new graph. So we'll represent negative 5 over here, way down here. This will be 5. And this here will be 2. We have the same second line. X minus 2 is the same function as we had in our bottom piecewise last time. So we can just draw the same line here. We include 2, and we go up to 5, but don't include it. So we have the same line here, but this line is slightly different. Here we have 2 minus x in the top instead of 3 minus x, and all that means is we're going to shift this down 1. So it's going to look something like this. As you can see, it's the same function as before, but everything is just shifted down 1. Oh, and once again, I forgot the negative here. I keep doing that. Negative 5, my bad. So once again, between negative 5 and 2, we have this negative x function, and between 2 and 5, we have this positive x function. Now, once again, I'm going to ask you, is this function, fn dot is function, continuous at x equals 2? We're looking at the same point as last time, but we want to see if it's now continuous with the change to the top function. You may notice that our endpoints are the same as last time, and we have a closed interval here with the function x minus 2 at 2, but an open interval here in the same spot with 2 minus x. Last time, the open interval and those closed intervals were stacked on top of each other instead of right on top of each other like they are now. And while we have an open interval here, we have a closed interval at 2 that fills the gap, if you will. So, purely based on visuals, yes, this is now continuous at x equals 2 because of two things. One, we no longer have two options, and two, even though we have an open interval here, we have a closed interval filling that gap. Therefore, it exists, and there's only one option. But because this is a math class, we should probably prove that mathematically. Once again, we're going to find the limit coming from the right side and find the limit coming from the left side, and if those two are equal, then the function is continuous at x equals 2. So, let's do that. The limit as x approaches 2 from the negative side would be coming from here to here, and the function that spans the negative side is 2 minus x. And coming from the right side, we have the limit as x approaches 2 from the positive side, the right side, coming here to here. This function is x minus 2. This is equal to 2 minus 2, which is equal to 0. And this is also equal to 2 minus 2, which is equal to 0. And as you can see, these two are equal. And when the left-hand limit and the right-hand limit agree, then the limit exists at whatever this is. Which means the limit as x approaches 2 of our piecewise function is 0, meaning that the limit exists there, meaning that the function is continuous at x equals 2. Yes, a big ol' yes to celebrate the fact that it is continuous. I hope this video helped you out. Consider subscribing if it did, and also you should subscribe because I'm posting all of Calculus 1, all the lessons, and the playlist is here if you want to go watch some of the other videos. I'll see you guys in the next lesson.